Hey everyone! Today I want to talk about an orbital elements visualizer that I built using Rust. It runs entirely in the browser as a WebAssembly module. No server, no runtime dependencies, just a static HTML page with a WASM blob. I was originally inspired by this video from NASA's Scientific and Technical Information Program.
Nodes are points in a satellite's orbit which intersect the Earth's equatorial plane.
I highly recommend checking out the whole thing because it's really educational. My goal was to recreate this model and have it be interactable in the browser. So at the center of this model is Earth. It slowly rotates on its tilted axis, which is 23.5 degrees off vertical, matching Earth's actual tilt. The two flat-colored planes cutting through the scene are the equatorial plane in blue and the orbital plane in red. The orbital plane is the flat surface that the satellite orbit lies in. The angle between the two planes is the inclination of the orbit. Around the orbital plane, you'll see a dashed white ellipse, and that is the orbit itself. And now for the labeled elements. The ascending node, the yellow dot on the right, is the point where the satellite crosses the equatorial plane, moving from south to north. Imagine the satellite going around its tilted orbit, and twice per revolution it punches through the equatorial plane. When it goes upwards, that's the ascending node. The descending node is the yellow dot on the left, and that's the opposite crossing southbound. The line connecting them in yellow is called the line of nodes. It's the intersection of the orbital plane and the equatorial plane, and both nodes always sit on this line. Next is perigee, and that is the white dot on the dotted line. It's the point in the orbit that's closest to Earth. The argument of perigee is the angle shown by the orange arrow from the ascending node to the perigee point, going in the direction of travel along the orbit. It tells you how the ellipse is rotated within its own plane. And then we have RAAN, right ascension of the ascending node. It's shown by the orange arc that's sweeping from the ascending node over to a fixed reference direction in the equatorial plane, the green x-axis. RAAN is the angle measured eastward along the equatorial plane between a fixed reference direction in space, so think pointing at a distant star, and the ascending node. It tells you which way the orbital plane is facing in space. Two orbits can have the same inclination, but different RAANs, and they'll trace completely different ground tracks. Inclination is shown by the purple arc. It's the tilt angle between the orbital plane and the equatorial plane, measured at the ascending node. Just to give you some sense of scale, a 0-degree inclination is an equatorial orbit, 90 degrees is a polar orbit, and the International Space Station is at about 51.6 degrees. I originally wrote this project in JavaScript using Three.js, which is a really awesome 3D graphics library. It made it very easy to get something on the screen quickly. Three.js handles WebGL, camera controls, lighting, all of that stuff. So if you're doing 3D on the web and you don't really have a specific reason to go lower level, Three.js is genuinely great. Quick aside on WebGL. It's the browser API that lets JavaScript talk directly to your GPU. Without it, browsers can pretty much only draw 2D. WebGL opens up the full 3D graphics pipeline for you, including vertex shaders, fragment shaders, depth buffers, all of that. Three.js is essentially a friendly wrapper around that API, so you don't have to write the raw shader code yourself. So let me walk you through the JavaScript version of this code. The globe was just a few lines. Sphere geometry generates the vertex data, and setting wireframe equal to true on the material tells Three.js to draw only edges. No manual geometry, no index buffers. The planes were plane geometry with a transparent mesh basic material set to side 3 double side so that they're visible from both directions without having to render 2 meshes. The dashed orbit was 3 ellipse curve, which generates a list of points along an ellipse. You feed those into a buffer geometry and apply a line dash material, and Three.js handles the dash pattern automatically. The line of nodes was even simpler, just 2 points. The RAAN and inclination arcs were quadratic Bezier curves computed manually in a loop. Same math as the Rust version that you're going to see later on, just written in JavaScript. Labels were Three.js sprite objects with a canvas texture. The approach here was to draw the text onto a hidden HTML canvas element using the 2D Canvas API, then upload that as a WebGL texture and apply it to the billboard sprite. Every frame calls sprite look at camera position so that the sprite always faces the camera. That works fine, but it means every label is a separate WebGL texture upload and a separate draw call. The interactive camera was orbit controls with a dampening factor of 0.05 for the smooth deceleration feel. In total, the JavaScript version was about 387 lines. Most of the hard geometric thinking was delegated to the library. So why rewrite this in Rust? A few reasons. After hopping around a few programming languages, I'm actively going all in on Rust right now, and I wanted a real project to work on, not just toy exercises. Rust also compiles to WebAssembly natively, meaning that the exact same code runs in the browser and could run natively on the desktop if I ever wanted that. And I was curious how the performance would actually compare, and I'll get into those performance numbers at the end. So yeah, the crate that I decided to go with for 3D graphics in Rust is 3D. It maps closely to how Three.js works conceptually, which made the mental translation easier. You have a context, which is the WebGL context, a camera, a mesh, an instance mesh, and a color material. Geometry is represented as a CPU mesh, which is a struct holding the vertex positions, the normals, and the index buffer, and you upload that to the GPU. On the GPU question, WebGL itself requires graphics hardware, so there's no automatic CPU fallback inside 3D. In practice, this doesn't matter too much. WebGL is supported on essentially every device, including cheap integrated graphics. And historically, Chrome would fall back to a software rasterizer called Swift Shader if hardware acceleration wasn't available. But that automatic fallback has been deprecated. Chrome will now fail to create the WebGL context instead of silently downgrading. If you're running in a headless or GPU-less environment, you'd need to explicitly opt in to Swift Shader via the command line flag. The one failure mode is if WebGL context can't be created at all, in which case window.gl panics. The console error panic hook crate, which I put in this project cargo toml, that catches it and writes a readable message to the browser console instead of silently dying. The entry point is a window.render loop call, which takes a closure. That closure runs every frame and receives the frame input with an elapsed time and input events. It's conceptually the same as Three.js's request animation frame loop, a function that gets called once per frame forever. The difference is that this is Rust, so the bar checker is watching everything you do. What that means in practice is the closure is moved, so it takes ownership of all the scene objects, so the camera, the meshes, everything. Nothing outside the closure can touch them after that. And inside the closure, every time you mutate the camera or pass it somewhere, the compiler is statically verifying that no two things are trying to modify the same data at the same time. In JavaScript, you just reach out and grab whatever you needed, but here the compiler is proving at build time that the data access is safe. And luckily, that actually catches a whole class of bugs before the code ever runs. The build tool is trunk. You point trunk at your index.html, it compiles the rest to WASM, generates the JavaScript glue via WASM bindgen, and bundles everything into a dist folder. One command, one static folder. One thing you'll notice if you open up the browser console, though, is a red uncaught error on startup that says, using exceptions for control flow. Don't mind me. This isn't actually an error. So that's WASM bindgen intentionally throwing and catching a JavaScript exception during initialization to probe the browser's runtime capabilities. It always shows up in red in DevTools even though nothing is actually wrong. You can't suppress it from your own code because it's inside the generated glue.js, so yeah, you're supposed to just ignore it, but it still really bothers me. There's also a yellow warning. The integrity attribute is currently ignored for preload destinations that do not support sub-resource integrity. Trunks generated HTML includes a link rel preload tags with integrity hash attributes. That's a security feature that would let the browser reject a tampered WASM file. Chrome just doesn't support SRI checks on preload links for WASM yet though, so it just warns you and moves on. The file still loads and runs fine though. One thing I had to figure out from scratch was the globe wireframe. In Three.js, you can use sphere geometry and set wireframe equal to true, and it just works. In the version of 3D that I was using, there was no wireframe mode, because initially I was using 0.18. A later version of 3D, though, 0.19, that did add a wireframe type. But it works by rendering every triangle edge of whatever mesh you hand it, including barycentric coordinates in the fragment shader. So if you pass it a sphere, you get every triangle edge, including the diagonals across each quad, so it looks triangulated rather than a clean lat-long grid. Not exactly what I wanted. So either way, I had to build the geometry myself. The first approach was to generate a set of polylines, one polyline per latitude parallel and one per longitude meridian. Then convert each of those line segments into a scaled cylinder. The 3D crate has an instance mesh type that lets you upload one base mesh plus a list of transformation matrices, and it renders all of them in a single draw call. So I had one cylinder mesh and 2016 transform meshes, one per segment. But I immediately ran into a visual artifact. Every latitude tube crosses every longitude tube at a right angle, and the cylinder end caps, the flat disk at each end, physically protrude into the adjacent tube at every grid intersection. Where two surfaces occupy the same region of space, the GPU has to pick what fragment wins the depth test, and the answer changes actually as you rotate the camera, because the geometry is right on that boundary. It looks like the globe has these little ugly spiky hairs that are sticking out at every crossing, and they drove me crazy. So I tried a few things. First, I added a depth prepass. The second sphere at 97% of the Earth's radius rendered before the wireframe, but configured to write only to the depth buffer, not the color buffer, only rendering front faces. The render states for that look like this. So that solved the back hemisphere bleeding through the front, because the depth buffer now has values at 97% radius, and the back wireframe tubes are at 100% radius, and those fail the depth test. I also set the wireframe itself to right mask color, no depth writes. That means the wireframe tubes don't fight each other in the depth buffer, since only one of them, the prepass sphere, is writing depth. But the hairs at the grid intersections persisted. The root cause was the cylinder end caps. CPU mesh cylinder in 3D generates a closed cylinder with a flat disk cap at each end. So at a 90-degree crossing, if you extend the segment by the tube radius so that the cap is buried inside the adjacent tube, the disk still protrudes. Geometrically, you can't fully hide a circular disk inside a perpendicular cylinder of the same radius. The math just doesn't work out at 90 degrees. The fix that actually worked, though, was to throw out the instant cylinder approach entirely and build one single smooth parametric mesh for the whole globe. Each latitude parallel is a torus, a donut shape. Instead of joining cylinder segments end to end, you parameterize the whole ring at once with two angles, one sweeping around the full latitude circle, the other sweeping around the tube cross-section. The result is one seamless surface with no joints, no end caps, and no intersections. For the meridians, the arcs running from pole to pole, the key insight is that each meridian lies in a flat plane through the Earth's center. The axis perpendicular to that plane is constant along the entire arc, so the tube cross-section sweeps from pole to pole with a fixed orientation. No twisting, no special handling at the poles. All 31 latitude rings and 32 meridian tubes get built into one mesh and uploaded to the GPU once. One draw call, no hairs. Getting the triangle winding order right, the order vertices are listed per triangle, is what makes the surface normals point outward correctly. I verified each one by checking that the normals point radially away from the Earth's center. That solved the visual problem. But the parametric mesh was still rendering around 16,000 triangles for what is visually just a grid of lines. Three.js's wireframe, that uses GL lines, single pixel hardware line primitives, which are dramatically cheaper to rasterize than the filled triangles. And I wanted the same thing in Rust. 3D 0.19, though, doesn't expose GL lines directly through its high-level API, but the context underneath is a thin wrapper overglow, which is the raw OpenGL WebGL bindings. The program type has a public draw width method that lets you pass in a raw draw closure. So I upgraded to 3D 0.19, implemented the geometry trait manually, providing the vertex shader, the bounding box, the transformation, and then I called context draw erase lines directly inside that closure. The geometry dropped to just pairs of Vec3 endpoints, 31 latitude circles at 64 segments each, plus 32 meridians at 64 segments each. That's 4,032 line segments, about 8,000 vertices, and 0 triangles. So after a while, I was testing this across different machines and doing the whole install rest, install trunk, add WASM 32, run trunk serve. That all just gets old very fast, so I Dockerized it. The Docker file is a two-stage build. Stage 1 uses the official Rust 1.87 Slim image to compile the project. It installs trunk with cargo install trunk locked, and that locked flag is important because some trunk dependencies had version constraints that broke with a different resolver behavior in Rust 1.87. Then it runs trunk build release, which compiles the rest to WASM with op level 3 and link time optimization enabled. Both of those are set in the cargo tunnel, and that produces a dist folder of static files. Stage 2 copies just that dist folder into an nginx image. I used nginx nginx unprivileged alpine rather than the standard nginx image because the standard one runs as root. The unprivileged image runs as a non-root user on port 8080, which is a meaningful security improvement for anything you'd actually deploy. Now you just clone the repo, run docker build -t orbital elements, and docker run -p 8080, and it pretty much works on any machine with Docker. No REST toolchain required. And the running container sits at about 14 megabytes of memory because all it's doing is just serving static files. All of the rendering happens client-side in the browser. So I was playing around with it, and I noticed that the model still felt a little laggy during rotation. The render loop was running fine, but the interaction felt sluggish. The culprit was DOM access from WASM. The diagram has 10 floating HTML labels that need to track their corresponding 3D points every frame. The axis labels, the node labels, the arc labels. The original code called document get element by ID inside the render loop for each one. Every one of those calls crosses the WASM to JavaScript boundary because WebSys is just a thin wrapper over the browser's DOM APIs. The boundary crossing itself has a lot of overhead. So 10 labels, 60 frames per second, 10 DOM lookups per frame, that's 600 get element by ID calls per second, each one triggering a WASM.js boundary crossing, a DOM tree traversal, and a JS WASM return. So the fix for all that was to collapse all of these crossings into one. I added a small JavaScript helper function in the index HTML that caches the DOM elements on the JS side and accepts all 10 label positions as a single float32 array, 2 floats per label. On the REST side, I precompute all 10 label positions as pixel coordinates into a flat array each frame, creating a 0-copy float32 array viewed directly into the WASM memory. No heap allocation, no copy, and call the function once. 600 get element by ID calls per second became one function call per frame. The label positions themselves are computed from 3D world coordinates using the view projection matrix. For a point in world space, you multiply by camera.projection times camera.view, divide by clip.w to get a normalized device coordinates in -1, 1, then convert to pixel coordinates. If clip.w is 0 or negative, the point is behind the camera, so the label gets moved off screen. This is also a meaningful difference from the Three.js label approach. In the JS version, the labels were sprite objects, so actual 3D scene objects that Three.js renders as part of the scene graph. In the Rust version, though, labels are plain HTML elements positioned with CSS transforms. That means that they're crisp at any screen resolution, and they work with browser accessibility tools, and you're not paying for a WebGL draw call per label. So how does the overall JS versus WASM performance compare? I recorded Chrome DevTools performance profiles of both versions, the JS production build, minified and bundled via Vite, and the REST WASM release build, and I just compared those two. On the CPU side, they're actually tied. So WASM scripting came in at about 54 milliseconds per second across 2 runs, versus the JavaScript version's 52. That 2 millisecond difference is within measurement noise, and if you look at just the application code, WASM's render loop is actually running about 15 milliseconds per second compared to Three.js's 18. The tiny remaining gap in total scripting is the cost of every WebGL call crossing the WASM boundary inside 3D's render pipeline, which is irreducible without changing the library itself. The GPU side is where WASM pulls ahead much more clearly. With the tube mesh approach, WebGL rasterization was about 1.7 times as expensive as the JavaScript version. The reason is that the REST version was rendering about 16,000 triangles just for the globe grid, while Three.js, that wireframe mode, uses GL lines, which is the single pixel line primitives that are dramatically cheaper to rasterize. So after I switched to GL lines in the REST version, which required implementing the geometry trait manually and calling the raw WebGL draw call directly, I profiled it again. The GPU painting time dropped from about 727 milliseconds per second down to 310 milliseconds per second. So that's roughly a 57% reduction, and it puts the WASM version about 29% below the JavaScript version's GPU cost. So WASM ties on CPU but wins on GPU. So yeah, that's the project. A REST WASM Orbital Elements Visualizer, compiled with trunk, served by nginx in a Docker container, with a GeoLines wireframe globe drawn through a custom geometry implementation. You have orbit inertia that matches Three.js's dampening fill, and label updates batched into a single WASM to JS boundary crossing per frame to keep that CPU overhead competitive with the JavaScript version. As always, the GitHub link to the code is in the description below. If you have any questions about any of the specifics, feel free to drop them in the comments below. Thanks for watching. Bye!